afternoon, everyone. Thank you for coming. The work I am presenting under the title Carbon Fiber Epoxy Composites Reinforced with Carbon Nanofibers has supervised by the Profs. Abílio Silva and Paulo Reis and is part of my doctoral work. I am going to start with an introduction to the work, followed by the mechanical characterization carried out, the presentation of the results, and the main conclusions. We know how important the application of composite materials is in various industries, particularly carbon fiber reinforced polymers, for example, in the aeronautical industry, larger and lighter aircrafts, the automotive industry, weight reduction and improved structure construction, lighter, stronger and more durability structures. But it also has its weakness, such as fragility of the polymer matrix, viscoelastic behavior, such as stress, relaxation and creep in polymer composites occurs even at room temperature, the fiber matrix interface and the resins to interlaminar shear strength. The main of this work is to improve the static properties of carbon fiber reinforced polymers by adding the optimum amount of carbon nanofibers. Here we can see some of the properties of epoxy matrix, carbon nanofibers and bidirectional carbon fiber fabric applied in this work. This diagram shows the stage of optimization and manufacture of carbon matrix and laminates. The laminates are manufactured using the hand layup process. 3-point bending tests were carried out and the phenomena of strain rate, stress relaxation creep and interlaminar shear strength were carried in accordance with the respective standards. In terms of epoxy matrix, the optimum quantity depends on their properties. C-common matrix bending stress increases by 11.3%, bending stiffness is around 30.1%, bending deformation decreases with increasing load 5.41%, Ebalta with 0.5 by hand percent of carbon nanofibers, the bending stress is 11.3% higher, bending stiffness 60.2%, bending deformation decreases with increasing filler 5.78% when compared with the neat matrix. In terms of strain rate, the final properties depend directly on the deformation speed, both in the net matrix and in the matrix reinforced with carbon nanofibers, and the response in terms of bending stress and bending stiffness with the addition of carbon nanofibers is positive. In terms of creep behavior, the addition of carbon nanofibers proved to have a direct influence of the material's behavior when compared to the neat matrix, as we can see in 3-point bending test after 3 hours of tests. The same applies to stress or relaxation behavior. In the final figures, it is possible to compare the net resin with the nano-exchange resin behavior after 3 hours of test. Two mathematical models were applied, kappa WW and Finlay, in order to predict the behavior of the matrix at a given understanding loads as a function of loads applied. Good results were obtained with the range of the dispersion values and with the fairly low error. Similar tests applying the same models were carried out for 100 hours, trying to predict the material behavior based on the 3-hour tests. We can see the theoretical results were within the range of the practical results. Similar studies have been carried out on carbon laminates. C-comin with 0.75% by hand of carbon nanofibers increased 20.4% in terms of bending stress from 752.2 megapascals to 905.3 megapascals. The stiffness increased 11.4% and the deformation decreased 3%. A balta with 0.5% by hand of carbon nanofibers increasing 12.5% in terms of bending stress from 756.2 megapascals to 805.9 megapascals. The stiffness increased 8.8% and the deformation decreased 4%. In terms of strain rate, this depends directly of the strain rate applied to both control and nano-exchanged laminates. The nano-exchanged laminates improved the properties in terms of stress and stiffness. In these graphs, we can compare the creepy behavior of the control and additive laminates with carbon nanofibers for 3 hours of tests for various applied stress. The similar for stress relaxation tests for 3 hours tests and various applied deformations. The same models were applied, obtaining theoretical results with the dispersion of practical results, and errors compared to the practical results kept low. The tables contain the parameters calculated and estimated by the two models for the different loads studied, as well as the theoretical and experimental values after 3 hours and their respective errors. As we can see, by applying the models, it is possible to provide creep and relaxation results close to the theoretical results for longer periods of time, for example 100 hours. In terms of interlaminar shear strength properties, the addition of carbon nanofibers reinforces the properties of carbon laminates. The interlaminar shear strength value for those using the C-MAST matrix reinforced with 0.75% by hanger of carbon nanofibers is about 8.6% wider, while for the Balta matrix reinforced with 0.5% by hanger of carbon nanofibers, it is about 9.4% wider. Main conclusions. Regardless of the epoxy matrix, wider values of added carbon nanofibers led to higher bending stresses and stiffness in the matrix and laminates. The best content by Weiger was 0.75% for C-MAST and 0.5% for Ebalta. Regarding sensitivity of strain rate, regardless of the matrix and nanocomposite, it was observed that both matrices and laminates are sensitive to strain rate. The bending stress and stiffness increase for wider values of strain rate. In terms of creep behavior and stress relaxation, both phenomena provide to be strongly dependent of the level of load applied. In terms of interlaminar shear strength, the best results coincide with those from the static bending point. Thank you for your attention.